Okay, so let's review what we covered in our last lecture. In our last lecture, we talk about the last part of this more on-chain rule and more on mutual information, right? In particular, we talk a bit about this conditional mutual information, right? And then we introduce you the Jensen's inequality, so which is one of the 4 most important inequalities in information theory. Right, just let me know if you cannot hear me very well, okay? So, yeah, here, we know that the condition will reduce entropy, right? And again, so it is not clear whether the condition will reduce mutual information or not, right? And we give you 2 examples here. So in one example, which is special case 1, so we show that the condition can increase mutual information, right? So the intuition here is that we assume X and Z here are independent, right? And then basically knowing Z, so it can help you to resolve more information of X by observing Y, or by observing both Y and Z, okay? And the other case is the case where the mutual information can the condition can reduce the mutual information, right? The reason of that is, so we form a Markov chain here from from Z to X to Y, right? And here, so basically this is the definition of a Markov chain, okay? So basically it means that, so if the probability of y given x equals the probability of y given x and z, right? So observing z will not give you additional more information basically, right? And in this case, you can see that, so now z depends on both x and y, right? Therefore, for given z, then so it's unclear, how the mutual information will behave, right? And we can show that, so now given z, so actually the mutual information will be reduced, okay? So this is 2 very important examples about the condition on mutual information, right? So basically we need to remember this very well. And then we cover the Jensen's inequality, right? And here you can see that when we talk about Jensen's inequality, we focus on the convex function, right? So hopefully everybody remember what convex function is. It's like this, right? So it's like a parabola, this kind of function, or and then the negative of a convex function will give you a concave function, right? Like for example, a log function, okay? And for convex function, and we have this formula, right? If we take expectation on a function of some random variable, right, and then it will be bigger than or equal to the function of the expectation, okay? And if it's concave function, vice versa would be true, okay? And we say if fx is strictly convex, right? So you can imagine that, if function is strictly convex, intuitively there will be only one minimum point here, okay? So that's one example here. And so the equality will hold if and only if when x is a constant basically, right? So it has to be equal to expectation of x with the probability 1. Okay, so that will be that will be the Jensen's inequality, and we're going to use it a lot in our class. Okay, and one direct application of it is that, so we can prove that the relative entropy between P and Q, so that will be bigger than or equal to 0, right? So we directly use the Jensen's inequality to prove that, and so the equality will hold when P and Q are equal, okay? So that's basically what we covered in our last lecture, okay? And today, let's see what we're going to cover for today. Okay, let me open my iPad. All right, just stop me if you have any questions, okay? So you can just speak up. Okay, so today is our lecture number 9. And we'll continue talking about Jensen's inequality. Right, and then we'll move to the second inequality, which is log sum inequality. Okay. Yeah, very nice. Okay, and yeah, since we know that for the Jensen's, using the Jensen inequality, we can prove that the relative entropy is bigger than or equal to 0, right? So we're going to use this theorem to show another very important theorem here. Okay, so the first one. So that's again still the Jensen's inequality. Okay, so we're going to prove an important theorem. So that's basically, it's called the cardinality bound. Okay, it basically to tell you, so what is the upper bound of the entropy. Okay, we sort of have seen that before. So yeah, what we have seen is that, you know, for the binary entropy function, so I have shown that it's upper bounded by log 2, right? So basically that is the cardinality bound. We're going to extend it to the general case, okay? So here again, we let x be a random variable. Okay, and then similar to before, we assume that it takes values in finite side, okay, of x of cardinality this, right? So here we use this this kind of absolute value to indicate the cardinality of a set, okay, right? And then we can show that the upper bound of entropy of x is given by this, okay? So that's the cardinality bound, okay? All right, so and here, so we need to be careful on this equality sign again, right? So we need to make sure that we know when the equality will hold, okay? So now you may take a guess, right? So the equality will hold if and only if, so can anyone tell me, so when the equality sign will hold, right? Think about the binary example, right? When the probability is kind of like a half, and then so we achieve the cardinality bound, right? So in general, can you tell me when the equality sign will hold? Yeah, anyone want to say something? Yeah, hopefully you're still there. So I can now see my Zoom. So hopefully I'm still on Zoom. Yeah, how can I? Yeah, if wait. Yeah, can anybody say something to make sure you're still there?
Yeah. Hello.
Yeah.
I'm here.
Okay, so you can still see my screen, right?
Yes.
Yep.
Okay, great. Yeah, because I can, yeah, when I share that, I cannot see the Zoom indicator anymore. So, okay, great. Yeah, so basically the equality will hold if and only if x is a uniform over the set of x, right? Okay, so basically, intuitively, that kind of makes sense, right? Because when x is uniformly distributed, right, basically means so every realization or every outcome will have the same probability, right? Then the entropy will achieve the maximum. Okay, so sort of makes sense. Okay, so now let's prove that, right? Okay, yeah, let's think how can we prove that? Right, so basically the way that we're going to prove that is to use what we just learned before, right? So what we know now is that the relative entropy is bigger than or equal to 0, right? By using the Jensen inequality, right? So basically we're just using that property, right? For example, let's see. let Qx, when we want to use the relative entropy, we need two distributions, right? So one distribution is the distribution of x, right? And the other distribution is, think about that what we're going to use, right? So we know that, from this theorem, so we can guess, right? So basically, this achieves the maximum when it is a uniform distribution, right? So basically, we like Q to be a uniform distribution. And then we want to compute the relative entropy between P and Q, right? So that would be the idea, right? And we know the relative entropy is bigger than or equal to 0, and then somehow we can derive this inequality, okay? So let's see how we can do that exactly. So let Qx be the uniform distribution, be a uniform distribution. So if it's finite set, right, so that would be like the only distribution here. Be the uniform distribution over x. Okay, and let our px be the PMF of x. Okay, and then we know that the relative entropy between P and Q, right, that's bigger than or equal to 0. So that's from our last inequality, okay? Okay, and given that, so we basically want to compute that, right? So basically, that's given by this, log Px over Qx, right? And we know that the Qx is a uniform distribution, right? So the Qx equals to 1 over the cardinality of x, right? Cardinality of the set x, right? Here's calligraphic. Okay, and then we can see that, so this will equals to nothing but this, right? Px log Px, right? And then we need to subtract this term, right? Minus x in x, Px log. So basically now in the denominator we have 1 over x, right? So this will go up. So this will be equal to that, okay? Okay, and here we can see that. So this will equals to, so the first term, if you see that, so if we have a negative sign here, so that will give you the entropy, right? The first term will be negative entropy, right? And then what is the second term? Okay, so second term here is that, so the cardinality of x is fixed, right? It's a constant. Then we just sum over all the px here. So summing over all the px here will give you 1, right? Therefore, the second term will be nothing, but it will be just, let's see, there's something. Yes, 1. Okay, here. So basically, we need to minus this 1 over cardinality of x, right? If we write in this way, right? So we need to make this sign a plus sign, it's not a minus, right? Because minus log 1 over x, right? And we take this one out, and here it becomes a plus, all right? And then we add log cardinality of x, right? And therefore, we can see that, so minus entropy plus that will be bigger than or equal to 0. Therefore, so we move the entropy on the left-hand side. So entropy will be less than or equal to the log of the cardinality of x, right? So that's basically, right? And then we can conclude that, so this guy will be less than or equal to log cardinality of x. Okay? And again, so the equal sign here, clearly the equal sign will hold. So if and only if, remember when the equal sign will hold for this, right? This equal to 0, right? That is when P and Q are equal, right? So in this case, P and Q are equal basically means that Px equals to Qx equals to 1 over the cardinality of x, right? For all x in x. Okay, then we finish our proof. Okay, this is how we prove that. All right, so, and also another application of this fact that the relative entropy is bigger than 0 is given by this theorem, right? So we kind of seen this theorem before, but so I'll just state it. So this is called the independence bound on the joint entropy. Independence bound on joint entropy, right? So we have not seen this exactly, but so the proof is very straightforward by using something we know very well. So this means that so the joint entropy of a vector of random variable, right? So that will be less than or equal to the summation of the individual entropy. Okay, so and it's kind of obvious why this is true, right? Hopefully all of you should be able to see that, right? We just need to expand it using chain rule, right? And then use the fact that condition reduce entropy, and then we can get that, okay? So proof is relatively straightforward. And here, again, we need to be careful on this equality sign here. So this happens with the equality if and only if. So you may imagine, right? So that happens when the condition will not reduce the entropy, right? That basically means that all the x's has to be independent, right? So when this vector has independent components, okay? So that's this theorem, okay? So let's prove that. So the proof is, again, so we just describe it, right? We need to expand it using chain rule. Hxi given Hxi minus 1, right? So this step is because of chain rule of entropy. Okay, and then we use the fact that so the condition will reduce entropy, right? Therefore, item-wise, so each of them will be less than or equal to xi, and then we prove that, right? So this is very easy. And then now we may think again, okay, so why the conditioning reduces entropy, right? So this is because so the mutual information, right? So we know that the mutual information between xi and xi minus 1, so that's equal to xi minus hxi given xi minus 1 on the top, right? And we know this guy is bigger than or equal to 0, right? Therefore, we can conclude that the condition reduces entropy, okay? And the reason the mutual information is bigger than 0 because mutual information is a special kind of relative entropy, right? Special case of the relative entropy, and the relative entropy is bigger than or equal to 0, right? Therefore, you know, the theorem that we're using to prove that is just a theorem that we have seen before, right? So it's this guy, right? Relative entropy is bigger than or equal to 0. Okay, so that's the logic. All right, so yeah, these are some of the theorem that we have seen. So that's directly apply the Jensen's inequality, and we're going to use Jensen's inequality a lot of time in our class, right? So now let's take a look at the second important inequality. It's called log sum inequality. So we do not use this equality very much in our class, or even in information theory, but we do need that to prove some very important properties, right? And then we'll just use those properties. Okay, so let me introduce you what is the log sum inequality. Okay, so first we need to see some negative numbers for non-negative numbers. For some non-negative numbers, a1, a2, up to an, and b1, b2, up to bn. Okay, so we have two set, right? An, from a1 to an, and from b1 to bn, right? And then based on this, we have Okay, the following. It's kind of weird. So let's see what's the meaning of that exactly. So if we sum from 1 to n, and then we'll have ai times log ai over bi. Okay, so this guy is bigger than or equal to this guy. Okay, so basically now we have the sum of all a here, and then log in the numerator, so that is this, okay, which is the same as this guy, right? And in the denominator, we have a summation over all the bi's, right? It's kind of very abstract, inequality, right? So it'll become more clear when we apply that to some other inequalities, right? So, and again, so we need to be careful on the equality sign. So this will equal. The equal sign will hold if and only if. So ai and bi. So it is a constant. Okay. Yeah, that's how. That's a log sum inequality. Okay. Right. You can see we have log, we have sum. Right. That's where the name coming from. It's called log sum. Okay. So yeah, so before applying that, let's see how we can prove that, right? So, unlike the Jensen's inequality, the proof is directly from the definition of the convexity of the function, right? So, relatively straightforward, but here, so it's less straightforward. So let's see how we can do that. So the key idea to prove this is also to use the Jensen's inequality, right? So this is another application of Jensen's inequality, right? And the key of using Jensen's inequality is that we need to find what kind of function fx we want to use, right? So here it's unclear, right? So, so let me tell you this. So basically what we're going to do is that we assume our fx or ft, so that equals to t ln t, or it's natural log. Right, so this is a function that we're going to use, right? So basically you can see, how we can use this kind of function, okay? And so let's see whether the function is convex or concave, right? So if we do a derivative of this function, so what we're going to get is what, right? It's a multiplication of two functions, right? Then we need to do a derivative of t and multiply log t, right? So that's log t, right? Because the derivative of t is 1. And then we need to add the second term, right? So which is t times the derivative of log t, right? The derivative of log t is 1 over t. T times 1 over t is basically 1, right? So that's the derivative of ft. And then, remember the theorem that we talked in our last lecture. How can we determine whether a function is convex or not, or strictly convex or not? We need to do the second derivative, right? So second order derivative is basically do a derivative of this guy, right? So that is just 1 over t. Okay, and here clearly remember that, so basically what we care about is everything is bigger than 0, right? All the a and t is bigger than 0, and clearly when t is bigger than 0, right? So it's bigger than 0 when t is bigger than 0, right? Clearly, so because it's bigger than or equal to 0, then we can conclude that ft is basically a convex, right? And when t is bigger than or bigger than 0, clearly, so this cannot be equal to 0, right? So basically, we can conclude that so ft is strictly convex. Okay, so from here we can conclude that hence ft or ft or basically just t ln t, so that is strictly convex, right? So here we can replace this ln by anything, right? So that will not impact the convexity. We just say for any log here, right? So that is convex. Okay, hopefully you are still following. So that's basically the function that we're going to use to prove log sum inequality. Okay, so now let's see how we can use it, right? So basically, yeah, let's write the left-hand side of the log sum inequality, right? So that's the summation of I from 1 to n, ai log ai over bi, right? So this is basically this guy, right? And then we're going to, try to basically use that, right? It's a convex function, right? So this should be, remember, so if it's convex function, what should be on the left-hand side, or what will be bigger? Right? A convex function look like something like this, right? So basically, the expectation of the expectation of the function would be bigger than the function of the expectation. Okay? So on the left-hand side, so we need to write an expectation of this function, right? And then we can use the Jensen, right? So the goal is to write expectation of ft, t log t, okay? Let's see how we can do that. Okay, and so basically, this so this form does not look like an expectation of that function, right? So let's see how we can manipulate that to make that as an expectation. Okay, so what we're going to do is as follows. So basically, we can see that. So inside this function is t log t, right? And here is a log a over b, right? So basically, we can think, this guy a over b as t, right? So therefore, so we can see that if this is like, okay, so we do not touch that, right? Then on the outside, right, so we need to write, some ai over bi, right, that's t, right, and then multiply some probability term, right? And so how can we do this, right? So basically what we're going to do is that we define something like this, bi over sum over bi from I from 1 to n, right? And clearly we imagine, so this term is a probability term, okay? And we let that equals to alpha I, all right? And then we can see that, so this bi and this bi can be cancelled, right? And we have ai here, so this term does not appear yet, right? So we multiply this guy in front, okay? And this is basically our manipulation, okay? And what we're going to do is that, so we let this guy equals to ti, okay? And alpha I is our probability, right? And then this is nothing but expectation of our function, okay? So that's basically the idea, right? Yeah, let's write it down. So basically we let ti equals to ai over bi, right? And alpha I equals to bi over this, okay? And then we can write down this, right? So from here we can see that, so now the summation over bi, so this term is separate, and for the rest of the term, okay, so we can write that as, I need to I think I missed something, right? So yeah, I forgot this, right? So basically we need to have another summation here. Yeah, let me fix it. So here, so basically we'll let that equals to alpha, and then so I miss a summation here, yeah, from 1 to n, okay? So now we have this summation from 1 to n, right? Now we have alpha I times ti log ti, okay? And clearly for this term, okay, so that's nothing but expectation, right, of t log t, okay? Or, that's the yeah, so basically that's our expectation. So we can also write that as expectation of our notation is f capital T if we treat T as a random variable. Okay, so yeah, so now we write the left-hand side as an expectation of some function, right? And now, since it's strictly convex, right? So we know that this guy is bigger than or equal to by using the Jensen's inequality, right? So here, still red. So here should be bigger than or equal to, right? The first term didn't change, right? Still have this. And then, so we need to write down the function of expectation. Okay. Okay, so this is a function of the expectation, right? So now we need to write it out. Right, so our function, remember what is our function? Our function is t log t, right? Then the function of expectation is to replace the t by expectation of t everywhere, right? So that's expectation of t and the log expectation of t, right? So this is definition of the function of expectation, okay? And so now what we need to do is we need to plug the value of t, which is small t, right, in here, right, and continue our computation. Okay, let's use a new page. So that equals to the first term, so still there, so we just keep it. From 1 to n bi, right, and the second term is the expectation of t, right, so that's nothing but sum alpha I ti, right? And then the next term is the log of expectation of t. Okay, so this is what we got. Okay, so now let's plug the value of alpha in and the value of ti in, and then we'll see what will happen. Right, so basically now alpha is the probability, right? So bi over sum over this guy. Yeah, normally we use a different letter here, right, instead of I, but here I think there's no confusion, so I just keep using that to make our life easier, right? T is AI over BI, right, and the log, again, the same thing here. BI over summation. AI over BI. Okay, so now, yeah, let's see. So what can we cancel here, right? So for example, right, this guy and this guy can be canceled, right? And this guy and this guy can be canceled, right? And this guy and this guy can be canceled, right? And see what we left here, right? So basically the first term is nothing but AI, right? And then inside, so we have a summation here, right? That's over AI, right? So basically now we have a summation on the numerator and then another summation in the denominator. Okay, and then we're done, right? So that's basically the log sum inequality, right? Remember on the, so yeah, maybe yeah, let's write it again, right? To remember it. It's kind of long here, right? So basically, yeah, from here our conclusion is that this guy is bigger than or equal to this guy. Okay, so you can see that what we did here is that, right, so if we have summation here and then we put the summation of A and B in the upstairs and downstairs, and then so this inequality will hold. Okay, so the last thing we need to double check is when the equality will hold, right? So here the only inequality here we use is here, right? So we need to be, and here we use Jensen, right? Okay, So, and we need to see when the equality sign will hold, right? So because fx is strictly convex here, right? Then the equality sign hold if and only if the random variable is a constant, right? Here our random variable is this capital T here, so it only happens when t equals to the expectation of t. Okay, so that's it's a constant. Okay, this basically means that a over b is a constant, right? Because a over b is basically our random variable here. Okay, so basically then we finish the proof of our log sum inequality, right? Because here we say so the equality will hold if and only if this guy is a constant, right? So we're done. Okay, so any questions?
So can I? You can go ahead first.
Yeah. Do you have a? Okay.
So can you remind me again what? So you're using Jensen's inequality. Can you remind me what f the function here?
Oh yeah, it's t log t. So here, yeah, it's kind of yes,
I see.
yeah,
Yes.
yeah, t log t, right? So basically t log t. So this is our function. Yeah.
I see.
So this is our f.
I see.
Yeah.
Yeah. So about that t log t, how does the sigma alpha I t log t becomes expectation of t log t? Can you do that again, please?
Yeah, no problem. Yeah, because so this function, so that's this function is ti. Sorry, this function is very good. This function is fti, right? And then expectation of a function is so here is basically the definition of it, right? Alpha I is a probability, right? So alpha I, so this is probability. Okay, so the probability of I is happening multiply fti, and then sum of that would be give you the expectation, right?
Oh, okay.
That clear?
Thank you.
Yeah, so this is basic definition. Okay, yeah. Yeah, so yeah, any other questions? Okay, great. So just stop me, right? Anytime if you have a question. It's kind of confusing.
I have one more question actually.
Yeah, no problem.
So you're saying so this is equal. The equality is the case because when f is strictly convex, and that's what you're showing, that when a over I is when a over I over b over I is constant, f of x is strictly convex.
Yes.
And so
wait.
they're equal.
Yeah, so it's a reverse. So here we show ft is strictly convex, right? So when it is strictly convex, and then so the equality holds only if t is a constant.
Because in that case, f is here is
so f still the same.
Strictly convex.
Yeah,
okay.
yeah. So yeah, f is strictly convex. So f is strictly convex is the requirement, right?
Yes.
Yeah, if that is the case, then this will hold, right? But if f is not strictly convex, then so we do not have that, right? The reason is that so if it's strictly convex, so there's only like one minimum point here, for example, right? So that's an easy way to think about it, right? For a parabola, it's only one minimum point, right? But if it's not strictly convex, so we can have a number of, minimum points, right? Then it may not hold.
Yes, I understand. Yeah.
Okay.
Okay, so yeah, so in this case, f is strictly convex, but it's equal when ai over bi is
constant.
Constant. So I suppose that would be like a 1-point distribution.
Exactly. Yeah, it's a Kronecker delta distribution basically. Let's say, if t are all integers, it will be a Kronecker delta distribution, something like that.
I see.
Yeah, does that make sense?
Yes.
Okay, great. So any other questions? Okay, great. For the, we have 8 minutes left. So now we're going to use that to prove some of our most important inequalities, one of the most important inequalities here. Okay, so let's introduce that. So now, so in information theory, so it is extremely important to know the property of entropy function, the relative entropy, mutual information, and so on. Okay, so and we're going to see, whether those functions are convex or concave. Okay, so things can be very complicated, right? Because you can see that. So for example, the relative entropy, we have P there, we have Q there, right? And things can be very involved. So let's see what do we mean by that now. Okay, so the next topic is that we want to see. We want to see the convexity or concavity of information quantities. Okay, so the first one is to see entropy, right? Because that's the simplest one, right? So yeah, now think a little bit. So is entropy function a concave function or a convex function in the probability? Okay, so we have seen one example before, so which is the binary entropy function, right? So if we consider two random variables, right, and they follow a Bernoulli distribution, then the entropy function is given by this guy, right? Log and 1 minus p log 1 minus p. Okay, so this is basically the binary entropy function, and we sketched it before, so it looked like this, right? So let's see, here is p. So basically we have this, right? The highest point is half here, and the value of this point is 1. Right, very good. Okay, and from here, clearly, I think we can conclude that, the shape is like this, right? So it's a, opposite of convex, so this is a concave function. Okay, so the binary entropy function is a concave function in P, right? But now, so let's try to generalize it, right? If you want to generalize it, so we have, so here the reason, so this is so easy is that, so we only have 2 items in the probability, right? Two items. And so I have P and 1 minus P here, right? So we just have one variable here basically, right? Because we need to make sure that, P plus 1 minus P has to be 1, okay? Let's say if we denote this guy as P1 and this guy as P2, and clearly we need to make sure that P1 plus P2 equals to 1, right? Okay, and basically from this figure we can see that it's a concave function in its probability, right? So actually, so we can generalize that, right? So basically the entropy function is always concave. So then we need to prove the concavity of entropy. Okay, so here the variable here, so we use this notation to denote a vector, right? So that's basically a vector of P1 and P2, right? This is a vector. Okay, so basically it means that entropy is convex in P, in vector P. Okay, so we're going to prove that. Okay, so what I've seen before for the convexity or concavity is only for a scalar, right? Not for vector. Okay, so now we need to extend the definition of a convex function from scalar to vector. Okay, So let's write it down. Convexity, so vector form, vector format. So we say if fx, right, and this notation again, so it's a vector notation. So this means that we consider vector of x1, x2 until xn. Okay, so we say this function is convex if for any two vector x and y in R n, okay, the dimension is n here, okay, and we need a number here, lambda, so that is between 0 and 1, okay, and then the inequality that we have seen before holds, right? So basically it means that alpha multiply fx plus e1 minus alpha fy, so that will be bigger than or equal to. So this is the expectation of f, right? And then it will be bigger than or equal to f of expectation. So inside is lambda times x plus 1 minus lambda y. Okay, so then, so this is basically the definition of the convexity. Okay, and by using that, so we can show the following theorem. Okay, so we denote that as theorem star. Okay, so we're going to come back to this. So this theorem shows you the concavity of entropy. Okay, so we consider hx as a function of p, right? So this basically means that this p is the probability vector associated with px. Okay, because it's a PMF, right? So we can write all the probability as a vector. Okay. So since we consider this hx as a function of p, then we can basically write the entropy as hp. Okay. So then we say that we can see that this guy is a concave function in P. Okay? Yeah, that's basically our theorem, right? So we do not show that exactly now. So what we're going to do is that we're going to show a more general form of it, right? Let's write it down. So so this is the first theorem. And then the second, so we're going to prove this theorem and then use the result of this theorem to show the concavity of entropy, right? So this is the convexity of the relative entropy or divergence. Okay. So the convexity of divergence. Okay, so this can be a bit tricky here, so let's read it very carefully. So we're going to prove that in our next lecture. Okay, so we consider a divergence P and Q, okay, so as a function of P and Q, okay, and P is a probability vector associated with Px and Q is a probability vector associated with Qx, okay, and then we consider them together, you know, as a big vector, okay. Okay, as a function of this, okay, where P is the probability vector associated with Px, and Q is the probability vector associated with Qx. Okay, therefore, because of this, so we can, think this guy as the relative entropy between, like this, P and Q. So we can use this notation to denote the relative entropy, right? The P comma Q, okay? All right, and then, so this guy, the relative entropy or the divergence, so this is a convex function. In PQ. Okay, and we can see that because entropy can be written as the divergence between Px, can be written in some form of Px and Qx, right? Where we can take Qx as a uniform distribution as before. Okay, so if we know this guy is a convex function, right, and then we can conclude this guy is a concave function. So the idea is something like that. Okay, and in the next lecture we're going to show this theorem, right? And the way to prove this theorem is to use a log sum inequality, okay, to prove that. All right, okay, so yeah, I think we have to finish today. So for the entire week, this week, probably we're going to have online lectures. Okay, so if our classroom is ready, then I'll send you an announcement, right? Otherwise, for this week, so we only have online lectures like this. Okay, yeah, and thank you so much. See you.
Thank you.
Yeah, bye.
Goodbye. I have a quick question.
Yeah, actually. No problem. Yeah, go ahead.
Px of scale.
Oh, sorry. Let me share it. Yeah, go ahead.
Oh, is p of x a scalar value in this case?
P.
In the divergence.
The value of divergence is scalar. Yes.
Okay, but is p of x a scalar?
P of x, yeah. How can I say it? So for Px is a scalar, but we view that as a vector, right? Because we are writing a small x here, right? Then it means so this is definitely a scalar, right? But we can view this function as a function of the vector of P and Q.
I see, which is a vector of essentially probabilities.
Exactly. So yeah, we can view the whole probability as a vector, right? And then it's a different viewing of this function, but nothing has changed here.
Okay. Okay, that makes sense to me.
Yeah.
Yes. Okay. Thank you.
Yeah, no problem.
Oh, also, like, when will there be homework?
Yeah, there will be homework. Yeah, I'll upload the homework today. So, but you probably or sometime this week, but you will not be able to do all of them yet. So it will be chapter 2. So we're going to have one homework for each chapter.
Okay.
Yeah.
Sounds good.
Yeah. No problem.
Okay.
Yeah.
Thank you so much.
Yeah. Thank you. See you.